Hello students, this is my lesson 2 on the series electrostatics. Yesterday in the first lesson you have learnt about how to charge a body, what is charge, its properties, Coulomb's law and its vector expression, and we also did what are the different kind of continuous bodies that may be present and how to measure it. My today's lesson is the continuation of yesterday's topics. The first one is electric field, its definition, its expression for point charges, vector expression of electric field due to a point charge. Then force due to a multiple charge and a multiple number of charges means this is a theoretical topic, but mostly the numericals come from this topic. Electric field lines and its properties. Here some subjective question may come. Electric dipole and electric field due to a dipole. It's an important topic from the examination point of view. Concept of flux. It's a very important topic for subsequent lessons. Torque on a dipole in uniform electric field. It's very important from examination point of view. Last but not the least, there are some memorization trick and self-evaluating quiz along with the questionnaire. So I start with the electric field. Electric field is a region of space around a charge or a system of charges within which other charged particles experience electrostatic force. Theoretically, electric field extends up to infinity, but practically it's limited to a certain distance. You must understand what is that limiting distance. The limiting distance depends on the value of the source charge, the charge which is producing the electric field. Now, the magnitude of the electric field strength, that is electric field strength or electric field intensity and electric field, remember it's a vector quantity because it's a force. So I define it. Electric field strength at a point in an electric field is the electrostatic force per unit positive charge acting on a vanishingly small positive test charge placed at that point. What is vanishingly small test charge? The vanishingly small test charge is one such a small charge that it does not actually manipulate the electric field at that point. I show you with a small diagram. Say plus Q, that is called the source charge which produces the electric field, and Q naught is the test charge, this is the vanishingly small test charge. Then the force will be repulsion, so it will be F, the repelling force, and that will be the direction of electric field as well. Similarly, if there is a minus Q source charge and a Q naught a test charge, then the force and the electric field intensity both would be towards the minus Q. You'll be learning about it. The electric field intensity is given as F by delta Q, where the delta Q limited to a very small value. Or simply you can write E is equal to F by Q naught. Here the Q naught has to be always put with its proper sign for any numerical. The test charge considered to be vanishingly small because its presence should not alter the configuration of the direction of electric field. Electric field is always along the direction of the electrostatic force. Electrostatic force on a negatively charged particle will be opposite to the direction of the electric field when it is the source charge is negative. Electric field is a vector quantity whose magnitude and direction are uniquely determined at every point in the field. Its SI unit is now electric field due to a point charge. There is a calculation here. E is equal to F by Q naught. Three-dimensional is in Newton and Q naught is in Coulomb. So that's, and we are taking at plus Q the source Newton charge per Coulomb at O, whereas a point arbitrarily chosen P whose coordinates are X, Y, Z shown as here, and OP, that is R, that would be the position vector. R would be equal to I cap X plus J cap Y plus K cap Z. Q naught will be placed at point P in order to find out the value of electric force as well as electric field intensity. force exerted on q naught, in that case would be F is equal to 1 by 4 pi epsilon naught q into q naught by r square, and that is the unit vector r. What is unit vector r? Unit vector r is a unit vector along the direction of the position vector r, that is along the direction of OP. Or you can say 1 by 4 pi epsilon naught q naught by r cube into vector r. Here r cube is coming because of the numerical value of r cap. R cap is equal to the position vector divided by its modulus of r. So this r cube is coming because of r square and r being multiplied. But remember that still F is inversely proportional to r square and F is not inversely proportional to r cube. So it follows the inverse square law. Electric field strength here is E is equal to F by Q naught. Therefore, ER means E at the point R is 1 by 4 pi epsilon naught q by r cube vector r, or this can be also written as 1 by 4 pi q by r square into unit vector r. There is a graph showing the variation of E with r square. It's a rectangular hyperbola. You can also draw a graph between E and r. It will have the same pattern, but its slope will be different. Try to guess how it will look like. I'm not giving it here. The electric field due to a point charge is always having a spherical symmetry. What is the meaning of the term spherical symmetry? Spherical symmetry means it is symmetrical, that is same along all direction at equal distance. When q is greater than 0, then the field is radially outward, and when q is less than 0, that is if it is negative, then the field is in terms of coordinate inward. Is given as E is equal to 1 by 4 pi epsilon naught. Now the vector r can be also written as xi cap plus yj cap plus zk cap. That's its, and modulus of these is root over x square plus y square plus z square. So r cube will stand as x square plus y square plus z square to the power 3 by 2. Superposition principle. The electrostatic force experienced by a charge due to other charges is the vector sum of the electrostatic force due to these other charges as if they are existing individually. You can understand electrostatic force and electric field both are vector quantities, so their sum will be also following the vector law of addition rather than algebraic law of addition. So you can see there are some test charges q1, q2, minus q3, plus q4 and minus q5. Now the force due to q2 due to q1 is given as F12. Similarly, force due to q3 due to q1 would be attracting, so it will be F13 and it's towards minus q3. Now force due to q4 is F14, which is away from q4 because it's repulsion, and q5 it is minus q5, so the force F15 will be towards the direction of F15. The net force would be F is equal to, okay, there's a vector sum, F would be equal, this F is F1 because it is force on q1, and it would be equal to F12 plus F13 plus F14 plus F15. It's a vector addition. You can write this in this format also. Then in the present example, A is equal to 1 because q1, and B is equal to 2, 3, 4 and 5. If we want to find out the force on the second charge, which is q2, then it will be F2. Actually, you have to understand about the floating charge. A will be 2. The charge on which the influence due to other charges is to be found assumed to be floating charge, and others are rigidly fixed. Like say in our only one example we have given that force on q1, so q1 would be the floating charge, and q2, q3, q4 and q5 would be fixed charges. So superposition principle will hold good for electrostatic field as well. because electric field is nothing but the electric force on 1 coulomb charge. Electric line of force, it's an important topic once again. Electric line of force is an imaginary straight or curved path along which a unit positive charge is supposed to move when free to do so in an electric field. Electric line of force do not physically exist, but they represent a real situation. And we are taking two cases. One is a straight electric field, another is a curved electric field. Now for the straight electric field line, the electric field intensity is always along the direction of the electric field line, but when it is a curve, then it would be a tangent drawn at the particular point electric field intensity is intended. We are talking about electric lines of force due to point charges. Q is greater than 0, it means Q is positive. The direction of the electric field lines will be radially outward. You can understand, because plus Q naught and plus Q, they are repelling each other. Similarly, if Q is less than 0, that means it's negative, then electric field lines will be directed towards. Representing electric field in terms of field vector, the size of the arrow represents the strength of the electric field. If the arrow is longer, electric field intensity is also higher in magnitude. You can see there are some other cases based on the previous example representing electric field line in terms of field lines. Electric lines of force due to a pair of equal and unlike charges, means one positive, then other one is negative. Here we have taken plus Q, then other one will be minus Q. So plus Q and minus Q, that is actually also called a dipole. You'll be learning about it. The direction of the electric field lines will be like this. P is any arbitrarily chosen point. If you want to find out the electric field intensity at P, you have to draw a tangent, right? You are drawing a tangent, and the dotted line will represent the boundary of the electric field intensity. This electric field boundary. Now we will be taking another case, electric line of force due to pair of equal and like charges. Like charges means both of them are positive or both of them are negative. So here we are taking plus Q and plus Q. So the direction of the electric field line will be just as shown. Here there is a dotted line you can see at the middle. That will be the point where there is no electric field existing. That point N, it is also the neutral point, and the dotted line will show you the electric field lines of force due to a uniform field. We can see the uniform field are the parallel lines which do not change in magnitude with distance, so its value remains constant, usually produced by a pair of equal and opposite charge plates as inside a capacitor. I'm now talking about properties of electric field lines. The first property, the electric field lines or the lines of force are imaginary lines. They actually do not exist, but there is a numerical value associated with it, which would be clear when you do the Gauss's law. There are 1.129 into 10 to the power 11 number of field lines associated with 10 to the power 1 coulomb. That is about 10 to the power 11 number of lines coming out or going in for 1 coulomb of charge if it is plus or minus. A unit positive charge placed in electric field tends to follow a path along the field line if it is free to do so. If it is not free to do so, it may not follow the electric field line, like if it is having some initial velocity. So it will be accelerated along the direction of electric field. You can see, of course, we have shown 1 coulomb charges moving along the direction of the electric field. The electric line of force emanate from a positive charge and terminate on a negative charge. So you can see they emanate out from positive charge. The tangent to an electric field line at any point gives the direction of the electric field at that point. If the electric field line is not a straight line, maybe a curved line, in that case only the tangent will give the direction of the electric field at that point. You can see that point P. If I want to find out what is the direction of the electric field, you have to draw a tangent there. Electric field lines can never cross each other. It's a very important property. If they do, then at the point of intersection there will be two tangents. Two tangents means two electric fields. But electric field is a vector quantity, so its sum will be always a single electric field, which is not possible if there are two directions. So for the electric field being a vector quantity, there can only be one resultant at the given point, represented by one tangent at the given point for the given line of force. Okay, electric lines of force are closer, that is more crowded, where the electric field is stronger, and the lines spread out where the electric field is weaker. So due to the COVID-19 infection, you are not to crowd, so you are not to take very strong electric field. Here we are maintaining social distancing, so it is where the electric field is weaker. Okay, it's on a lighter note. You can see this plus Q, the Q is greater, so the electric field lines are strong, and here plus Q is also a plus Q. The small q is a smaller charge, so the field lines are far away. It's a weaker one. Capital Q is greater than small q. Electric lines of force are perpendicular to the surface of positively or negatively charged body. In the positively charged body, they are emanating out, and negatively charged body, they are going inward. In fact, here we are showing a pair of charged bodies. There's a positively charged thin sheet, so the electric field lines in either direction going out, and you can see they are parallel lines, so this is an uniform electric field. Now let us see a charged volume, but here remember it is a conductor, so there is no electric field inside. All electric fields are outside. Electric field lines can contract lengthwise to represent attraction between two unlike charges. The point number 10, the number of lines of force per unit cross-sectional area perpendicular to the field line that is also known as density of line of force or flux density. It is found directly proportional to the magnitude of the intensity of electric field in that region. Say there are delta n number of electric field lines in a certain region, and there is a small area delta A, then the number of field lines, that is delta n passing per unit area, that is delta n by delta A, is proportional to the electric field intensity E. Here electric field lines, that is electric force, lines of force, cannot pass through a conductor. Just in the previous slide we have given some hint, as the interior of the conductor is free from influence of electric field. So there are two pair of electrified charged bodies, like say positive and negative charge plates. So electric field lines should start from positive and end at negative, but if you put one solid or hollow conductor, the electric field lines will come out from the plate and emanate out from the other end and go terminate at negative plate, but inside the conductor, whether it is solid or hollow, there is no electric field line crossing. This is a very important aspect. This is also called electrostatic shielding. One example, if you are sitting inside a car is a metallic body, and there is a lightning, you will be saved from the bolt because you are inside a conducting body. So there is no electric field inside. It's called electrostatic shielding. Here I want to tell you a very important information, that if there is a +1 coulomb charge somewhere, the number of electric field lines that is emanating out from there is 1.129 into 10 to the power 11. I repeat, 1.129 into 10 to the power 11 number of field lines that will be coming out. If it is a -1 coulomb charge, then equal amount of field lines, but that will be going in. If there is a 2 coulomb charge, in that case it will be double of this number of line, that is 2.259 into 10 to the power 11, and so on. So the number of field line also depends on the strength of the source charge. Electric line of force can pass through an insulator. Electric dipole. Electric dipole is a pair of equal and opposite charges separated by a very small distance. So the electric field produced by a dipole, called the dipole field, and electric dipole moment is a vector quantity. Electric dipole moment you need to understand in some other ways as well. It's a vector quantity used to measure the strength of an electric dipole. And let us show one electric dipole. There's a -q charge, there's a +q charge, and they are separated by a small distance. Here, for certain reason, we're calling this as a twice L. Then the dipole moment will be directed from -q to +q along the direction of the line joining. P vector would be written as q into twice L. So its magnitude is charge into the separation between the two charges, and I cap shows that is the direction. It's a vector quantity. The magnitude of the electric dipole moment is the product of magnitude of either charges and the distance between the two charges. The direction is from negative to positive charge. SI unit of electric dipole moment is coulomb meter. A special note here, an ideal dipole is that dipole in which charges are very large. Dipole has got separation is very small. One is called axial line. The line which is the atoms are almost like an ideal -q and +q, that is called an axial line. And O here is the center of the dipole, and the two distances to L and L together makes the dipole separation twice L. And the point P, that is an arbitrarily chosen point along the direction of the axis, the axial point it is called, and we have to find out the value of the electric field intensity at the point. The distance between O and P is x. because B is positive charge, so it will be repelling test charge, so EB will be directed away, and EA, that is the force, that the field due to minus Q at A, little smaller in magnitude, will be towards PO. So the total electric field would be EP is equal to EB minus EA. Then we can find that electric field EP is equal to EB minus EA. EA is equal to 1 by 4 pi epsilon naught. The distance between A and P would be X plus L. OP is X and OA is equal to L. So it is OP plus OA, that is X plus L whole thing square. I cap shows you the direction. AB is 1 by 4 pi epsilon Q by X minus L square. That is PB. PB is OP minus PB. OP is X and PB is PB has to be found out. So it is BO is L. So it will be X minus L whole thing square. So the total electric field comes out to be P is equal to 1 by 4 pi epsilon naught Q by X minus L square. Here EB is stronger, minus Q by X plus L square. So the net electric field will be coming out to be that EP is equal to 1 by 4 pi epsilon naught 2 Px by X square minus L square whole thing square. This is for finite dipole. Remember, finite dipole is that dipole where the distance is comparable to the separation. But for an ideal dipole, L is very much less than X. In that case, EP will be equal to 2P 4 pi epsilon 2P divided by 4 pi epsilon naught divided by, and X square is X square minus L square will be almost equal to X square, X to the power 4, and numerator and denominator has got 1x, so that will be cancelling out. It will be 2P by 4 pi epsilon X cube. Here one more important point is EP is inversely proportional to X cube, and it does not follow the inverse square law. So I'll tell you spherically symmetric. You'll understand is also not spherically. The electric field intensity at a point on the equatorial line. So what is the equatorial line? If we draw a perpendicular at point O, O is the center of the dipole. So the perpendicular drawn from point Q to O, that Y, that is known as the equator. Q is an equatorial point. Now we can find out the electric field intensity EA due to minus Q at A and EB due to plus Q at B. The vector sum of EA and EB will be EQ. So let us find it out. Result in electric field intensity at point Q. EQ is equal to EA vector plus EB vector. So vector sum, their angle between them is twice theta. So EA and EB, they are equal because BQ is equal to AQ is equal to root over X square plus L square. So what you get, the electric field intensity by resolving EA and EB, you'll be finding EB sin theta and EA sin theta will cancel out, and EB cos theta and EA cos theta will add up to give you the net electric field. EQ is equal to EA cos theta plus EB cos theta. So that will be EQ is equal to 2 by 4 pi epsilon Q by 4 X square plus L square from EA and EB, and cos theta, it is L by X square plus L square to the power half. Again 2QL is equal to P, that is the dipole moment. So EQ would be equal to 1 by 4 pi epsilon Q into 2 L X square plus L square to the 3 by 2. So that is by 4 pi epsilon P by X square plus L square to the power ideal dipole 3 by 2. That is for finite dipole. X square plus L square will be almost equal to X square. So it will be EQ is inversely proportional to X cube. But one important thing, there's a minus sign appearing. Why this minus sign is appearing? Minus sign is appearing because P and EQ, they are oppositely directed. So you can find that it be here EQ would be P by 4 pi epsilon naught Y cube. Actually X is replaced by Y only to show that the axial distance and the equatorial distance are different, but of course here x and y, the magnitude if being same, you can see EP is double the strength of EQ. Actually, because of that, we call this one as a torque on the electric dipole symmetric uniform electric field, spherically asymmetric. That's a very important topic. The observation point is far away when the dipole is very short, then the electric field intensity point of the axial line is double the electric field intensity at a point on the equatorial line. Dipole that is placed in a uniform electric field, but this time it is making an angle theta with the electric field direction. Then there will be a pair of charges, and because of that there will be a torque experiencing. The torque would be given by the product of either of the parallel forces and the perpendicular distance between the two directions of the parallel forces. So it will be twice L sine theta. So torque is electric force into perpendicular distance. It will be tau is equal to QE into twice L sine theta. That is to Q into twice L is P, so it is P sine theta. So you'll get tau is equal to, the tau is a vector quantity, tau is equal to P cross E. Direction of torque is perpendicular and into the plane containing, here the right hand thumb rule is applicable. P cross E is directed inward. SI unit of torque is Newton meter. So you can see tau is P cross E when theta is equal to 0 degree, tau is equal to 0, so it's minimum. When theta is equal to 90 degree, tau is PE, which is maximum value, and theta is equal to 180 degree, then also it is tau is equal to uniform electric field. When electric dipole is placed in a uniform electric field, it experiences a torque and tends to align in such a way to attain a stable equilibrium. Equilibrium when tau is equal to 0. So you can see an electric field and a dipole, minus Q2 plus Q is P. When we rotate it by an angle from theta 1 to theta 2, that is theta 2 minus theta 1 is equal to delta theta, then the work done would be delta dW is equal to tau d theta. So tau d theta is PE sine theta into d theta, and if you integrate it over theta 1 to theta 2, that will be giving you the work done PE cos theta 1 minus cos theta 2. Remember, smaller the angle, larger is the size of the cos theta value. So you can understand, if potential energy is arbitrarily taken as 0 when the dipole is at 90 degree, of course it is not 0, but we can take for a uniform field it is almost equal to 0. Then PE in rotating the dipole and inclining it at angle of theta is given a potential energy is equal to, you can understand, theta 1 is equal to 90 degree, so cos theta 1 is equal to cos 90 degree is equal to 0, and cos theta is cos theta, theta 2 is equal to theta, that means U is equal to minus PE cos theta, which is the potential energy of a dipole taken at an angle theta. When theta is equal to 0 degree, U is equal to minus PE, that is minimum energy possible at theta equal to 0 degree. So that tells you about the stable equilibrium. Case 2, when theta is equal to 90 degree, then U is equal to 0, then it is not in equilibrium at all. Here we are about to conclude our lesson today. So this is the scheme of the revision. You have to note it down in your pages. I want to say thank you for watching a very long class today. Thank you all.